All right, welcome to The Explainer. Today, we're going to get into something super interesting. How do you hide a secret message inside a video? And I'm not just talking about sticking a little logo in the corner. No, we're talking about embedding data so deep that it's literally part of the pixels themselves, completely invisible. Okay, so here's the game plan. First, we'll touch on why you'd even want to do this. Then we'll look at how a computer sees a video, which is totally different from how we do. After that, we'll get into the nitty-gritty of hiding the message, figure out the magic trick that makes it invisible, and finally, see how you can actually pull that secret message back out. Let's do it. All right, section 1. Let's start with the big picture, protecting your digital creations. I mean, what's the point of all this, right? So, picture this. You pour your heart and soul into a video, it goes viral, and then bam, someone else just rips it, uploads it as their own, and starts taking all the credit. It's a creator's worst nightmare, right? And you might think, well, just put a logo on it, but those are so easy to crop out or just blur. We need something way, way smarter. And that's where this whole idea comes in. Digital watermarking. Think of it like a secret digital fingerprint. It's data that you weave directly into the media itself. So it doesn't matter who copies it, who downloads it, who shares it. That proof of ownership travels with your video forever. It's your claim, hidden right there in plain sight. Okay, section 2. So to really get how we can hide data inside a video, we need to kind of shift our perspective. We have to stop looking at video with our human eyes and start seeing it like a machine does. And how do machines see it? Well, they use these really powerful mathematical tools to translate all that pixel data into something else entirely, frequency information. And the two big ones we're going to talk about are the discrete cosine transform, that's DCT, and the discrete wavelet transform, or DWT. These are our keys to the whole process. Now, the DCT is really interesting. What it does is it changes the question. Instead of a computer looking at a bunch of pixels and going, okay, this one's red, this one's blue, it looks at a whole block of them and asks, what patterns and frequencies make up this little square? It's a total paradigm shift, moving from just color to the underlying structure. And this image just shows it perfectly. See, on the left, that's what we see, an 8x8 square of pixels. Then you run the DCT on it and you get what's on the right. Now that looks like another grid, but it's not pixels anymore. Those are called coefficients. And each number basically tells you how much of a specific pattern, like a smooth gradient or a sharp edge, is in that original block. The other tool, DWT, does things a bit differently. Instead of breaking things into patterns, it kind of decomposes the image into layers. You end up with one layer that's like the blurry main idea of the image, that's the approximation, and then you get all these other layers that hold the details, all the sharp lines and fine textures that make the picture clear. And honestly, there's this fantastic analogy for DWT that just makes it click. Think about when you're on a really slow internet connection and an image is loading. First, you get that super blurry, pixelated version, right? That's kind of like the approximation part. And then, bit by bit, the details load in and the image gets sharper and sharper. That's DWT in a nutshell. Okay, section 3. So we've got our tools, the DCT and the DWT. We know how to talk to a video in its own language of frequencies. Now, let's get to the fun part, actually hiding a message in the pixels. So this diagram pretty much lays out the whole roadmap. It's like a little assembly line. You start with your original image, you run it through what's called a forward transform, that's our DCT or DWT. Then you get to the crucial step in the middle. You modify that data. That's where you sneak in the watermark. And finally, you run it through an inverse transform to put it all back together into an image. Simple as that. So let's break that down, step by step. Step 1, you take a frame from the video and chop it up into tiny 8x8 pixel blocks. Step 2, you hit each of those blocks with your transform, either DCT or DWT, to turn those pixels into frequency numbers. Now step 3, this is where the magic happens. You take your watermark, your secret text or whatever, and you use it to just slightly tweak some of those frequency numbers. And finally, step 4, you reverse the process, turning those slightly changed numbers back into pixels, and voila, the video looks identical, but your secret is now baked right in. Right, moving on to section 4. Now, this leads to the biggest question of all, doesn't it? If we're literally changing the data that makes up the video, how is it possible that we can't see it? How is it invisible? Well, it is absolutely possible. And the secret, believe it or not, has less to do with complicated computer science and more to do with biology. It all comes down to cleverly exploiting the built-in weaknesses of our own eyes. Okay, here's the key. Our eyes are really, really good at noticing big, smooth changes, like the overall brightness or color of an area. That's what we call low-frequency information. But we are surprisingly bad at noticing tiny, complex, rapid changes, like the intricate texture of a carpet or the leaves on a tree. That's high-frequency information. We just kind of gloss over it. So let's bring that back to our 8x8 grid of numbers. That one number in the top left corner, that's called the DC coefficient. It's the big one. It controls that low-frequency stuff, like the average brightness of the whole block. All the other 63 numbers are the AC coefficients, and they handle all that high-frequency stuff, the fine details, the textures, the noise. And that is the secret. You hide the data in the places our eyes are lazy. You make tiny little changes to those 63 AC coefficients, the ones controlling the details we barely notice anyway. But you leave that super important DC coefficient completely alone. You don't touch the average brightness. And by doing that, you can embed your information in a way that is, for all practical purposes, completely invisible to us. Okay, final section. We've got our secret message embedded and invisible, but now how do you get it out? And even more important, is this thing tough? Can it survive being compressed, re-uploaded? What about if someone films your screen with the phone? Is it still there? Well, getting the data out is pretty straightforward, actually. It's basically the embedding process in reverse. If you have the key, meaning you know which transform was used and exactly which coefficients were targeted, you just run the transform on the video, go look at those specific spots, and read the changes to piece your hidden message back together. But what about that ultimate test, that camcorded video? I mean, think about it. When you film a screen, you're adding all this new noise, weird angles, compression from the new camera. You're basically attacking the original data. Can the watermark possibly survive something that brutal? And the answer for a well-designed watermark is yes. It's a huge challenge, for sure, but this is what we mean by a robust watermark. The secret is that you don't hide your message in just one little spot. You smash it into tiny pieces, and you scatter those pieces all across the entire video. In thousands of different blocks, using thousands of different coefficients, you spread the risk. That way, even if filming the screen totally messes up one part of the video, there are still enough surviving pieces scattered everywhere else for the algorithm to find them and put the original message back together. So that's really the big takeaway here. This isn't about slapping a logo on something. It's about fundamentally changing the language of the video, translating it from the simple language of pixels into the complex language of frequencies. And once it's in that language, you can edit it to carry a secret that's tough, invisible, and truly baked into the DNA of the file. And that really leaves us with a huge question for the future, right? As AI gets better and better at creating content out of thin air, how are we going to tell what's real and what's not? Technologies like this might be one of the keys, not just for proving who made something, but for proving that it was made in the real world at all. Definitely something to think about. Thanks for joining this explainer.